these are the main concepts that we're going to cover, tree, binary tree, and binary search tree. And the main point is that they're going to model hierarchical relationships. Now, the notion of hierarchy is different from what we covered last week in terms of linear data structure. When we talk about linear data structure, we talk about which data element is accessible. So it kind of have only one relationship, which is which item comes before which other item. Now, in a hierarchical form, things can actually be non-linear. That means that they can be non-linear in two different ways. One is in a hierarchical sense. Another one is a non-hierarchical sense. And these are the two structures that we're going to cover. Today we're going to talk about trees. We are going to talk about graphs later on after the midterm break. Trees essentially look like this, which are hierarchical in nature, whereas a graph looks more like a network. Now, what are some examples of hierarchical structures? One is your file directory structure. So there is a folder has subfolders. Each of the subfolders, again, has their own subfolders, and so on. Now, these are hierarchical in the sense that a folder may have a lot of subfolders, but any subfolder only has one parent folder. So in that case, you have this notion of branching kind of relationships, where for a given folder, there are many other branches you can make, but for any given one, there's only one way you can go back, which is back to the parent folder. Now, another example is a family tree. Now, but in this case, we're talking about an upside-down tree, where you first have the child. The child has two parents, mother and father, and the parents, each of them, has two parents, and so on. So then in that case, a given person has a lot of ancestors, right? But the relationship here always leads back to the same person. Another common example is organizational chart, like companies, right? So the companies has a lot of employees, and they need to manage their subordinates in a particular fashion to make sure they're going in the same direction. So this is Apple in the time of Steve Jobs. So Steve Jobs being the CEO, he's at the center. And then he has people who report to him. And then there are other people who report to those other people, and so on. So they kind of form a hierarchy. Now, the form of the tree essentially looks like this. So you have a structure where there is one object at the top, and then it branches out into multiple other objects, which again branches out further, and so on. Now, the node that is at the top, we call it the root node. And finally, there are the leaf nodes at the bottom, and the leaf nodes are the nodes that have no more downlines. So it kind of looks like a tree, but it's upside down. The roots at the top, the leaves are at the bottom. Now, when we talk about trees, there are certain properties or certain objects that we would like to be able to refer to. So one is, based on the structure of the tree, we can talk about having different levels. So the root node is at level 1, and then the nodes after that, below that is level 2, level 3, and so on. So then we can talk about the height of the tree, and the height of the tree will be the maximum level of any of its nodes. So in this particular case, level 1, level 2, level 3. So the deepest level is level 3, so we call it the height is 3. And then there are certain relationships that we are going to maintain within this tree. One, the most important one, is the sense of parent and child. So here, a parent can have multiple children, but a child only has one parent. And that essentially is the property of a tree. Now, you can talk about these relationships even in an indirect way, being ancestors and descendants. So an ancestor is indirectly linked to the descendants. So we would say that CEO is the parent of the VP operations, and CEO is the ancestor of the manager, HR manager, finance. So, and again, we can say that the manager, HR, and finance, they are the descendants of the CEO. And then there are siblings. Siblings are children of the same parent. So all the VPs are siblings because they all report to the CEO. Right? Now, we define a tree recursively. It's recursive in the sense that you define trees over other trees. Now, what is a tree then? A tree essentially is a root with a few children, and each of the child is again another subtree. So meaning that a tree is the root of children who are themselves subtrees. And now, what are each of the children? Each of them is a subtree, which means that each of them is a root of their own little subtrees. And then they have children who are again the roots of further subtrees below. Yes?
So it means the second level is the root node of the level.
So the CEO is the root of the whole tree. So it has a few children, the VPs, and each of the VP is the root of another subtree. So in this case, VP sales is the root of subtree 1, and then VP operations is the root of a subtree 2. This is the root of a subtree 3, and then again each under this, right? So you have the manager research. Again, this is going to be the root of another subtree, but this subtree happens to just have one node. Now we are going to talk about a specific type of tree. We're going to focus on this, and there are reasons why we do that. We're going to focus on what we call a binary tree. So the concept of a binary tree is a tree that where every node can have at most 2 children. So they can have 0, they can have 1, they can have 2, but not more than 2. Okay, now this essentially is a tree, but it's not a binary tree. So the earlier example, right, the tree with the CEO, where the CEO is a parent of 3 VPs, there are 3 children, so it's not a binary. Now, but why do we focus on binary trees? Because binary tree is a simplified structure, so we can define a lot of different algorithms that can run on binary tree that becomes more general. It becomes more general because a lot of the trees that are non-binary, you can still transform it into a binary tree. So for example, let's say you have the following tree, it's not binary because the CEO has 3 children, and you want to make use of an algorithm that relies on a binary tree. So you can transform this into a binary tree. You just need to make sure that every parent can have at most 2 children. So we tell the CEO, okay, so you cannot have 3 direct reports now, you can only have 2. So what the CEO may decide to do is to appoint another middle person. So maybe he will say, all right, so then let me get a senior VP that is going to take care of the operations and the technology, so that these 2 people report to the senior VP and the senior VP reports to the CEO. In that case, then you have converted it into a binary structure. And essentially, you still maintain all the hierarchical information, except that the structure is a little bit different, but the algorithm will likely still run perfectly fine. All right? So from now onwards, we're going to talk only about binary tree. Now, in the case of the binary tree, a node can have 0, 1, or 2 children. So there are different types of binary tree. So the first tree is what we consider full. So a full tree, it means that any node would either have 0 or 2 children. That means there is no node with only 1 child. So you either have 0 or you have 2. And we consider it to be a full tree. Now, we say a tree is complete if you go level by level. At every level, the nodes are full, except that the last level, so everything is completely filled from left to right. So there is no dangling things here. Now, for example, if this tree looks like this, where you don't have this child, right? So then there is a dangling one, which means that this node is not full, then it's no longer a complete tree. Now, so if you go to the full extent of completeness, you get a perfect tree. Perfect tree will be every leaf node is at the same level, and they're all full. So either have 0 or 2 children. That means that every node above is going to have 2 children, except the leaf nodes. They're going to have just 0. Now, once we have a tree, we can use it for many applications. So there are many applications of binary trees. Essentially anything that you want to represent as hierarchy, you can do it within a tree. So one of the important applications is in terms of implementing priority queues. Heap is a data structure that actually is related to the notion of binary search tree that we're going to cover later. Huffman coding, this is for compression. So if you want to express data in terms of smaller number of elements, you can use Huffman code or Huffman tree to do that. And the Huffman tree essentially is a binary tree that will transform data into a binary representation. Syntax tree, this is pretty common in linguistics or programming languages. When we try to analyze a sentence or a programming code, there is a hierarchical fashion in terms of how things are related to one another. And that allows us to represent a code, let's say in terms of a tree structure. Then this allows compilers, for instance, to process the code and to do things with the code. Now, the implementation of the tree is actually very simple because now that we see that it can be defined recursively, then essentially every tree consists of a series of nodes, and every node has a value, and the value is going to contain something about the node, and it also has two pointers to the left child and the right child. And that's one advantage of having a binary tree, because you only have two children. It's easy to call them. You call them the left, you call them the right. So there are no other, so left child, right child. Now, the notion of left and right, they are kind of arbitrary. So it's up to your definition to say which one is the left, which one is the right. But the point is that there is a specific way in which we can refer to the node, whether it's the left one or the right one. So then the left one here in this example is going to point to the root of another subtree, which again has two children. So in this case, it points to the right child to something else, and so on. Now, there are different kind of operations you can define on it. Some are access operations, like what is my left child, what is my right child, what is my value. Some are creating a new node, setting the left child or the right child, or deleting them. Or you can look at the structural things, like what is the root of the tree, or what is the height of the tree, how many nodes does it have, and so on. Now, once we talk about having a tree, you pretty much have a particular structure that can encode some hierarchical information. Now, the problem comes in terms of how do we actually process things on the tree. Now, earlier, we have been doing things with a list or an array, and clearly there is a way to go through the array systematically, and that's essentially iteration. So it's like a for loop, a while loop. You can say, let me give you the first element, second element, third element, and so on in an array. Now, but in a tree, there is no such thing as the first, second, third, because the nodes are not indexed. You cannot say, give me 3 and then colon 0 or something, right? So you can't access a tree like you do an array. So there must be a different way for us to be able to go through different elements of a tree. And this way is what we call traversal. Traversal essentially is an iterative way to go through different parts of the tree, and we want to do this systematically until we can get to every node in the tree. And there are essentially 3 different ways to do that. We call them preorder, in order, and the post order. So preorder means that we're going to visit the parents before the left child and then the right child. In order, the in there means in between, right? So the left child first, the parent in the middle, and then the right child later. And then post order means that the parents after the children. And we're going to define them recursively. Now we're going to look at each one of them. Now this is the first one, preorder. Now in the case of the preorder, you visit the node first before you go to the left and then to the right. But you need to keep in mind that this is recursive. So meaning, for example, if you start at the root, and for any traversal, we always start at the root. So you start at the root is CO, we will visit the root first. So number 1 there means that this is the first one visited. So after we visit CEO, we are then going to do traversal to the left. So then we call on the left one. Now, but this is recursive. So when you call VP1 then will start another recursive call. There's going to be another instance of this where VP1 is a node. Then we'll visit VP1 first. And then we're going to traverse to the left. So that means that then VP1 is going to call M1. M1 has no more children, so it returns to VP1, which will then call an M2. So this is 1, 2, 3, 4. Now we have to do all the left side first before we can go to the right. When you go to the right, you go to VP2. Recursively, it's going to go to M3. So then essentially it gives you a particular sequence of 1, 2, 3, 4, 5, 6. So if you do this traversal, you're going to get the nodes in this particular sequence. Now, this is the first one, which is preorder. So the second one is in order. Now, the notion of in order, if you examine the difference between the two, preorder here, in order here. In order, the visit happens between the left and the right. So meaning that we go to the left first, and then the parent, and then the right. So in this case, we start from CEO, but we can't visit CEO directly. So CEO says, go to the left first. So we go to VP1. The VP1 says, you cannot access me directly. You need to go to the left first. So then we will do M1 first, and then the parent, and then the right child. Now that we have done the left side, then we can go to the middle one, which is the parent, and then the right side. Now when we start the right side, we have VP2, but VP2 says go to the left first, so we go to M3 and then VP2. So it'll be 1, 2, 3, 4, 5, 6. And if you examine this and the preorder, they give you a different sequence of nodes that get read from the tree. Alright, now the final one is the post order. Now the post order is an order where you look at things, where you go to the left and the right first before you visit the nodes. So what it means is that you start from the root, but the root says go to my left, which is VP1. VP1 says before you visit me, go to visit my children first. So you go to M1 and M2 before you go to VP1. Then you're done with the left, then you need to go to the right. You start from M3 and then VP2 and then CO, which is the last one to be visited. Now, these are three traversal orders.